Dr. Jim Clarke from Intel, whose keynote is titled "From a Grain of Sand to One Quantum Bit of Information." Jim Clarke is the director of the Quantum Hardware Research Group within Intel's Component Research Organization. He was responsible for launching Intel's quantum computing effort in 2015. His group's primary focus is to use Intel's process expertise to develop scalable qubit arrays. Um, Jim has been very influential, working to influence the National Quantum Initiative Act since about 2018. He comes from a silicon microelectronics background, and specifically, he played a leadership role in Intel's technology development in interconnect research. So Jim holds a PhD in physical chemistry from Harvard University, and he has been with Intel since 2001. So Jim, it's all yours.
Great, thank you very much. It's a pleasure to talk to everybody today. I'm talking to you from my wife's Lego room rather than the labs today. I'll cede the labs to the engineers who are in there doing good work with social distancing. I'm going to talk to you today about quantum information, in particular quantum computing, with a focus on, say, an industrial perspective of a semiconductor manufacturer. And to do this, let me first say that quantum computing is just one architecture within Intel's portfolio of alternative architectures to get more out of compute. We have our conventional computing, and that continues. We have technologies such as deep learning and graph analytics that are coming to the forefront today. We have some longer-term projects such as neuromorphic computing, which we would expect to develop over the next decade. And then we have something like quantum computing that we would expect to develop over the next 10 to 15 years. So quantum computing represents just one of several really exciting different architectures that Intel is exploring today. Now, many of you on the conference are probably intimately familiar with quantum computing. I've always told the analogy using coins, and in particular, we highlight two concepts. The first is superposition, where imagine if you have a coin in a classical world, that coin is either heads or tails. It's one or the other. If it were a light switch, it would be on or off. If it were a bit of information, it would be 0 or 1. In the quantum world, it's best to think of that coin as spinning, as representing heads and tails with some probability at a given time. The second key concept is known as entanglement. And if you had two coins spinning on a table and they were linked, you could represent 4 states at one time, both heads, both tails, heads and tails, tails and heads. If you had 3 coins spinning, you could represent 8 states at the same time. It's exponential, 2 to the n states for n quantum bits of information. If you had 50 qubits, you could represent more states than just about any supercomputer on Earth could represent, and that's the basis for the quantum supremacy work that Google published roughly a year ago. If you had 300 spinning coins, or 300 qubits, you could represent more states than there are atoms in the universe. Now, a couple of holidays ago, when my whole family was in town, we had coins spinning on a table to see how long the coins would spin. The longest coins would spin roughly for about 10 seconds. But if we had up to 7 coins spinning between the 4 of us, the amount of time that those coins spinning together was just a second. And moreover, when the teenager gets frustrated with how his coin is spinning, he hits the table and all the coins fall over. This shows us that there's a certain fragility involved with these coins, or metaphorically with these qubits. And so we're actually going to need to do error correction and have many more than just 300 of these. We're going to need millions to do something useful. So what would we do that's useful? There are several things that our community is looking at, from travel and logistics to medicine, chemistry and drug design, climate modeling, financial portfolio optimization, and cryptography. And since we've had speakers from the government, obviously cryptography is certainly very interesting worldwide. So quantum computers will do things today that we just simply can't do with conventional computers, with supercomputers of any size and any accuracy in any amount of time. That's the power of quantum computing. So there are several ways to make a qubit, and I am not highlighting all of them here. I'm going to highlight just a few of them, and then dive into the ones that are perhaps most interest to Intel. And what you can see in the upper right-hand corner is a quantum bit of information precessing between its 0 and 1 state. The one I'll start with first is the trapped ion, where essentially you're studying or manipulating the excited states of a metal ion using a laser. This bears a lot of similarity to an atomic clock, which won the 2012 Nobel Prize in physics, and companies like Honeywell and IonQ are looking at that. The next one might be superconducting qubits, where you are essentially creating a nonlinear LC oscillator circuit to create an artificial atom, if you will, which you can then manipulate. This is the technology that's studied by companies such as Google, IBM, Rigetti, and D-Wave. The final one would be a silicon quantum dot, where effectively what you're doing is encoding the bit of information, the 0, 1, into the spin of an electron. And Intel and HRL are working on these technologies. And to go into this, we really need to understand the transistor. And so that's what I'm going to talk to you about next. So why spin qubits? Why are these interesting to Intel? Great article, probably about 7 years ago now, of mankind's greatest inventions. And if you take a look at this, semiconductor electronics are fourth, behind the printing press, behind electricity and penicillin. This is pretty good company. And so, you know, for the past 70 years, just about everything technical in the world has revolved around semiconductor electronics and the transistor. And so that's where I want to lead to next. The transistor is the most ubiquitous man-made object on Earth. At Intel, we think that we ship about 800 quadrillion transistors a year. That's an 8 with 17 zeros after it. That's a few transistors for everybody on the planet for every minute of every day. That's pretty impressive. There was an article in Forbes, I believe it was 2013 or so, that said by about 2025, we expect there to be more transistors on Earth than we even have human cells, which is just mind-blowing to me. Okay, so if when developing a new technology, we can rely on our basic transistor to help us get there, either as the device or controlling the devices we wish to make, we're going to be much farther ahead with the technology. So how do you turn a transistor into a qubit? Many of you remember what a basic transistor looks like on the left from your introduction to physics or electrical engineering classes. You basically apply a potential to a gate, and then you have a current of electrons flowing through the device. Okay. Now, imagine instead of having a current of electrons through that device, you have just a single electron. You operate it at a temperature and voltage where you have just a single electron trapped inside the device. If you put that device into a magnetic field, the electron can have one of two states, spin up or spin down, where the energy difference between these devices is set by the magnetic field. Okay. Now imagine just the way we string multiple transistors together, we string multiple quantum dots together, if you will, single electron transistors. And we get them close enough and we can control the applied potential of the devices so we can actually get these electrons to interact with each other. Each of these individual electrons represents a qubit. When we bring these together, we can have multi-qubit interactions. And hopefully just looking at this, you can see the similarity between a transistor and a silicon spin qubit. So what's exciting about this is that we can then rely on our technology that we use every day to fabricate advanced CMOS to fabricate our quantum dot and qubit lines. And at Intel, in Intel Oregon at our Ronler Acres site, which is our primary R&D site, we have a pilot line running on the same tools, the same technology, to build our quantum computing devices. This is 300 millimeter, and each wafer has approximately 100 die, and each die has several devices to test. And so with each wafer comes out, we think there are roughly 10,000 quantum dot or qubit structures to test. Now, these quantum dot structures, the way you manipulate them is that you have that electron underneath your gate. And that gate controls the energy or population of your quantum dot. And if you put that electron in a magnetic field, you can have either spin up or spin down. Well, the way you manipulate that between the two states is then to apply a short microwave pulse to the circuit. And that electron is affected by that microwave pulse and rotates between the spin up and spin down state. This is how you would generate what's known as a Rabi oscillation, or to manipulate that electron between the spin up, between the 0 and 1 states of the qubit, the heads and the tails of the coin. And at Intel, with our full 300 millimeter process, there's nothing academic, there's no E-beam. We can demonstrate coherent control of a qubit with really compelling coherence times. Okay, but just demonstrating a qubit is not enough to make a quantum computer. We actually have to control that qubit. And let me provide a couple of examples that should provide hope, but at the same time, really outline areas of focus. The image on the left, when I give a talk at a university, I like to quiz the students and see if they know what it actually is. The image on the left is the first integrated circuit. Okay, this was 1958. And as you can see here, I think it had only about 5 transistors. By the way, it took 12 years to go from the first integrated circuit in 1958 to the first microprocessor in 1970, and the timescales for the big inflection points in our industry have always been about that decade level. But what you can see here is it's something of a brute force method for generating and wiring up that circuit. Fast forward to last year and the presentation shared at ISSCC, you can see the number of wires necessary to control 50 qubits. Today, each qubit requires just a couple individual wires. So when I start this and say that you're going to need millions of qubits to do something useful to change your life or mine, it's not conceivable that we would have 1 million wires, physical wires, going into and out of a fridge or onto a chip. So the message that I want to give is that brute force interconnects work for a few devices, but not millions. So what we're doing at Intel is using our CMOS process to deliver integrated cryogenic qubit control. The image on the left is how you might wire up a qubit chip today. it would be inside a dilution refrigerator at a fraction of a degree Kelvin, and that you would have individual wires going outside of that refrigerator to racks and racks of electronics, which you would then coordinate with some sort of main controller. What we're aspiring to do with our qubit control chip is to bring this control inside of the refrigerator. From a form factor perspective, we can have fewer wires, or we can have more ability to wire the control to the qubit without having concerns about power and attenuation and filtering of the lines. So getting the control as close as possible to the qubit. To this effect, we have demonstrated what's known as our Horseridge control chip. Horseridge is the coldest place in Oregon, and so you can obviously see why we chose that name, given that we're doing cryogenic control in a fridge. This is based on our 22 nanometer FinFET CMOS technology. We would take the chip, we would package it, we would then put it on a PCB and install that in the refrigerator with individual wires down to the qubit control chip and relatively few wires outside of the fridge. Okay, so one of the messages here is that that even if it's not a spin qubit, all of the control will still rely on advanced CMOS for quantum computing. So don't declare that dead. In fact, it's critical to get this technology done. Let me just go over a few of the details of Horseridge. Horseridge has cryogenic drive capability for manipulating the qubits. It can support up to 128 qubits with frequency multiplexing. It has multiple channels. We can arbitrarily define what our pulses look like based on SRAM memory. And we have pretty wide frequency output of 2 to 20 gigahertz, which would make this ideal for either superconducting or spin qubit control technologies. And you can see a general design for this Horseridge. And then you can see some of the arbitrary pulse shapes that we've been able to generate along with the powers applied. Now, later this month, there's going to be an update with far more information on the actual qubit control. I'll wait until that happens before I share that here. But this chip is being actively used to drive qubits with matched performance to room temperature electronics. But with anything at Intel, we're not satisfied with one, and so just a quick little teaser here is that the second generation is coming, and we hope to share a bit more detail in about a month, and then a full publication of it at ISSCC in February. So hang tight. Okay, so I focused a bit on the qubit technology and the control technology, all of which bear similarity to transistors, but still, that doesn't give us a full quantum computer. We need a full stack. Now, any sort of computer has far more than just a microprocessor. It has the architecture, for example. So with a quantum computer, we have to recognize that we have a qubit chip, we have control electronics, we have the control processor, and these are some of the things I've spoken about. We need to find a way to map and schedule algorithms onto our device and run it effectively, taking into constraints perhaps the connectivity and the performance of the actual qubit chip in a way that lets us get the most information we can out of our device. So from a system-oriented design, we have to be workload-driven. We have to design our stack with some of the constraints around the qubit chip and control in mind. And then even before we get to the physical implementation, we have to be able to simulate the performance of our algorithms and to emulate our overall full stack. Some of the challenges that we have are obviously the qubit device design and the performance, the interconnect complexity, which I highlighted the need for making those wires more elegant, all within the framework of making this scalable. Developing a system for you today that might be a few tens of qubits but wouldn't scale to thousands or millions will slow us down. Clearly, we're going to have to deal with error mitigation and resilience of our algorithms and our qubits in order to realize or overcome some of the fragility that we have with our actual qubit devices. And then obviously how you map and schedule an algorithm based on some of the other challenges here will determine its overall effectiveness. Given that this is the Chicago Quantum Summit, I just want to highlight one of our first, I'll say, external engagements with Qnext, which is the DOE supported center at the University of Chicago in Argonne. And for this, we are going to put a full stack research test bed, first brought up at Intel, and then put on site at Argonne as the program develops. So I want to summarize. Quantum computing is one of many novel architectures being explored by Intel. Okay? But it's definitely an exciting one, especially as someone with the chemistry or physics background that I have. And we have to realize that we're pursuing a scalable quantum roadmap that's built on our silicon expertise. And that manifests itself not only in our choice of qubit, by how we're doing our control. And finally, it's worth mentioning that developing a good qubit or a good control technology in a vacuum of how you operate the system is going to be inefficient. And so we are taking a co-design approach to deliver an overall full stack. And I think with that, I will finish and let Supratik, if there are any questions.
Thank you very much, Jim, for giving an overview of what Intel is interested in the area of quantum computing, and in particular outlining the relevance of the interconnects here. I'll take one. I'll start off with one question from the audience, and the audience, if you have questions, please keep them streaming in. It allows me to edit them quicker. What is the time horizon for a scalable quantum device that will have robust error correction or fault-tolerant error correction built into it? When do you think this will be demonstrated, or the time horizon for it?
Yeah, so you can call my comment. I hope it's not unpopular. I think it's rooted in quite a bit of data, but we would guess somewhere around the time frame of 10 years before a quantum computer is doing something that would be useful, that would solve applications or problems that would be useful for everybody. And let me make a comment. If you take a look at the history of quantum compute, the history of compute, it took 1947 from the first transistor to the first integrated circuit. It took in 1958, and then 12 years later was the first microprocessor. The Intel FinFET or high-K metal gate technology, both, these are technologies that have affected the life of everybody on the planet, and they were released in successive generations with one another, or a couple of years apart, but each of those technologies took at least 10 years, sometimes 12, to realize the fruition. So I think it's unreasonable for something as challenging as quantum computing to expect it to go faster than a $500 billion worldwide industry on semiconductors and transistors. Thank
you. I'll take a second question, and I'm going to modify it a little bit because I know this is a very the subject close to your heart, Jim. Interconnect lines coming out of qubit chips are very dense. What do you feel is the most promising approach to overcoming this problem of densely packed microwave lines and qubits at cryo temperatures?
Yeah, so there are many ways to tackle this. Right now, the lines tend to be large coax lines, and there are companies out there looking to make these very dense. That is going to buy you some margin. The next thing that you have to do is to get control circuitry as close as possible to the qubit chip so that you could then use packaging techniques to get, which would have even higher density. And then beyond that, you would have to have, I'll say, on-chip control. So perhaps these are registers or muxes on the qubit plane. There you're being even a little bit more careful for energy and power, but the density would be even higher. And then finally, I think what you need to do is you need to figure out a way that you can have sort of shared wires, that you don't have an individual control wire for each qubit. So there's probably, let's say, naively, an order of magnitude for each of those four things, and it begins to scale up. But it will take some creativity and time.
Great. And I think finally, you come from a microelectronics background, Jim. You have vast experience there. What are the lessons that we can learn from there as we get into quantum information? And likewise, what mistakes should we not make?
Yeah, so I was thinking about this as I was listening to the last talk. In fact, what would be that advice? And again, this is we've had the semiconductor industry has existed for 70 years in some form, and it's a $500 billion industry. It would be easy for us as scientists to reward ourselves for the creativity of doing something completely different and trying to make a quantum computer. Perhaps more challenging is to find a way to be creative to use the technologies we do have to build a quantum computer. And so the more we can rely on what exists today, the faster we will develop this system. So I think I would just encourage people to, every time the idea seems just a little bit crazy, ask if there is a more straightforward path. I think in the long term, that'll be easier.
Okay, great. And with that, thank you very much, Jim, for
my pleasure.
Your plenary presentation. And we will now take a break until 12:30, so 15 minutes later, when we will promptly begin the Federal Centers and Institutes panel. So see you back at 12:30.